This will be the last of the stoichiometry topics, limiting reactants. As always, copy all of this into your notebook. Use the spacebar to start and stop as needed. All right, let's start with a couple of definitions. The limiting reactant or limiting reagent is the substance that is totally consumed in a chemical reaction. The excess reactant or excess reagent is the substance that is only partially consumed in a chemical reaction. Okay, let's look at a real-life example. Consider making a hot dog. I suppose this would be a real-life analogy. So making a hot dog. So you go to the market and you buy a package of hot dogs and a package of buns, hot dog wieners. And you open the package of wieners and you have 10. Open the buns and you have 8. So when you go to make your hot dogs, you've used up all of the buns. So it is the limiting reactant. Whichever reactant is consumed completely is your limiting reactant. For the hot dog wieners, we have 2 left over. We only used 8. So the excess reactant are the hot dog wieners. 2 are in excess. So just like a chemical reaction, you're going to have a couple of reactants. Sometimes you have more, but let's just go with 2. One of the reactants, like the buns here, will be used up completely. It'll be completely gone when the reaction is over. We call that the limiting reactant because it limits how much you can make. And then the other reactant, we're going to have some of it left over. It's the reactant that we say is in excess. Okay, now there's a PhET simulation on this. Let's take a look at it. It's kind of cool. Okay, so the sandwich one is just like the hot dogs we were just making. You can tailor your sandwiches as you might want, but let's just go with the default cheese sandwich, 2 pieces of bread, 1 piece of cheese to make a cheese sandwich. So at the beginning, so our reactants, let's say we have 8 pieces of bread and 5 pieces of cheese. Well, we can see that we were able to make 4 sandwiches. All of the bread was completely used up to make our 4 sandwiches, but we have 1 piece of cheese left over. So we would say the bread is our limiting reactant, used up completely, and the cheese, we had enough cheese to make more sandwiches, but we ran out of the bread, which limited how much we could make. The cheese is in excess. Okay, now there is also a actual reaction you can play around with. This is the synthesis of water. You can do ammonia or the combustion of methane. So let's say we have 6 molecules of hydrogen, and let's go with 4 molecules of oxygen. So we can see over in the product side, we were able to make 6 molecules of water, but we have some oxygen left over. So the hydrogen was completely used up. So it's our limiting reactant. It limited how much we can make. We had enough oxygen to make more, but we couldn't because the hydrogen was all gone. So the oxygen is in excess. Okay, now there's also a game you can play, so you can click on that and I'll let you play around with that if you'd like. So if the concept of limiting reactant and excess reactant is a little elusive for you, I would encourage you to play around with these simulations. I think it'll be helpful. Okay, I'm going to give you the 4 steps that we're going to use to solve limiting reactant problems. First, convert the mass of each reactant to the mass of a product that could be produced. The smaller mass produced is the answer. Requires 2 stoichiometric calculations. 2. Determine the limiting reactant. It's the reactant that produces the smaller amount of product. 3. Calculate the amount of the excess reactant used. Requires 1 stoichiometric calculation. And finally, subtract the mass of the excess reactant used from its initial mass to determine the amount left over. What we say is in excess. Now, all of this will make a little bit more sense to you as I walk you through a homework problem. Okay, now what I'm going to do is literally do the first of your 4 homework problems. So go ahead and just, in your notebook, write down homework, limiting reactants, problem number 1. I'll walk you all through it, copy it all down. This is your example problem to do the remaining 3. Okay, so the first. Methane undergoes combustion to produce water and carbon dioxide. Write a balanced chemical equation for this reaction. Phases are not needed. You might want to pause the video, see if you can write your balanced chemical equation, and then come back. Okay, the balanced equation. Methane, remember, in a combustion reaction, you have to have oxygen as a reactant, producing water and carbon dioxide, and so this is balanced. Next question, how many grams of water can be produced when 50 grams of methane reacts with 50 grams of oxygen? Now, this is completely different than the problems you've seen before. In all the problems you've seen before, in stoichiometry problems, you were given a certain mass of one of the reactants and asked about something else, usually one of the products. You were never given masses of 2 different reactants. And that's what's new here. You're going to need to figure out which of the 2 reactants is used up completely, and that's going to be the one that determines the amount of water that can be produced. The other reactant, you're going to have some of it left over. And so even though you might have more than might have enough to make more, you're not going to be able to make any more because the other reactant, the limiting reactant, was used up. All right, so let's summarize this question like we would do in a stoichiometry problem. We have 50 grams of methane, 50 grams of oxygen, and the question is asking us how many grams of water can we make. So we're going to have to first convert the grams of methane to grams of water, see how much the methane can make, and then do the exact same thing with the oxygen, see how much water the oxygen can make, and then compare the two. Okay, so the 50 grams of methane, we'll convert that to grams of water. Okay, so the answer here, 112 grams of water can be produced from our 50 grams of methane. But we don't know if we can make that much because we may run out of the oxygen before we make 112 grams. We know we have enough methane to make 112 grams, but we don't know if we have enough of the other reactant, in this case oxygen. So we need to do another complete stoichiometric calculation to determine the amount of water that the 50 grams of oxygen can make. So 50 grams of oxygen converted to moles, using our mole ratio from the balanced chemical equation. So the 50 grams of oxygen is able to make 28.2 grams of water. So let me make sure that you follow what's going on here. We have enough methane to make 112 grams of water. We have enough oxygen to make 28.2 grams of water. So the question is, well, how much do we make? Well, the answer is the 28.2 grams of water is how much is produced. And the reason is even though we have enough methane to make a lot more, once we've made 28.2 grams of water, the show is over. All of the oxygen has been consumed. So the reaction stops. The methane is in excess. We have more than enough methane to react with all of the oxygen. So when you do these 2 stoichiometric calculations, all you need to do is to look at your 2 answers, and the one that is the smaller is going to be your answer. So the 112, 28.2, 28.2 is smaller, that's the answer. And the other answer, I encourage students to just cross off. That never happened. You had enough methane to make that much, but you couldn't because once you made the 28.2 grams of water, the reaction stopped. You were out of oxygen. Okay, next question. Which is the limiting reactant? Well, it's always going to be the reactant that was used up completely, the reactant that made the smallest amount. In this case, it would be oxygen. So the limiting reactant is always the reactant that made the smallest amount of the product that you calculated. Okay, now the next question is going to ask us how much of the methane did we have left over? Which reactant is in excess and by how much? Now in the homework, it gives you the answers to this problem, so you can check to see whether you got it right. Okay, so what I'm going to do is use the balanced chemical equation again to kind of summarize what we need to do. We just calculated that we were able to make 28.2 grams of oxygen because of water, because the oxygen was our limiting reactant. So the oxygen was completely consumed in making the 28.2 grams of water. But what we don't know is how much methane was needed to make that 28.2 grams of water. So we're going to need to do another stoichiometric calculation to convert the 28.2 grams of water to grams of methane, to see how much we actually used. So there's two steps in answering this problem, this question. Step one, so this is our stoichiometric calculation, converting the grams of water to grams of methane. Okay, so the 28.2 grams of water required 12.6 grams of methane. That's how much was used to make the 28.2 grams of water. But that's not the answer to the question. The question is asking us which reactant is in excess and by how much. So how much was left over? Well, that's a simple subtraction problem. You simply look back to the very beginning of the problem, problem B. We had 50 grams of methane. And we just calculated that of that 50 grams, we used 12.6 grams. So all we need to do is to subtract that from the amount that we started with. So we have 37.4 grams of methane left over, or what we say is in excess. Okay, so let me kind of walk you through this again, make sure you're following this. From the previous problem, we calculated the amount of water that was produced, and we know the oxygen was the limiting reactant, so it's completely gone. But the methane isn't. And so this stoichiometric calculation told us how much of the methane was used to make the 28.2 grams of water. And then to determine how much was left over, we simply subtract that from the amount that we started with, the 50 grams of methane. Okay, so use this as your template example to do the remaining three problems. It's exactly the same steps, different reactions, different numbers, amounts, but exactly the same steps. Okay, that's it.